Hi, I'm Antonio Sala, and in this video we are going to discuss some last remarks about LMI sets, semi-definite programming representable sets, and we'll discuss affine transformations, and in particular, scaling and building cones that have that set as a section, and some kind of convex or interpolation between such LMI sets. With that set interpolation, at the end of the video, we will be able to show how to morph, let's say, an LMI set onto another. So we gradually transform an egg into a triangle, let's say. So let's go with the details. An LMI set was the set of feasible values of a given linear matrix inequality expressed, for instance, as this thing. So X will be a two-dimensional vector, and if this matrix is semi-definite, the values of X that render that inequality true will belong to the LMI set. LMI sets were convex, and they had polynomial boundaries. Good. As a last remark, we are going to use later on is the fact that even if we call them linear matrix inequalities, at least in control, in fact, it's an abuse of terminology, because actually they would be better called affine matrix inequalities, because this inequality has linear and constant terms. But okay, we will call it linear, but in fact, this thing can be decomposed in a constant matrix. If this is LMI of X, this constant matrix having all the terms that do not depend on decision variables is LMI of 0, plus this term with no constant terms, which is the actual linear stuff that if I multiply X times 5, then this matrix multiplies by 5. So this piece of the matrix will be denoted as LMI linear of X. And in fact, if this can be decomposed as these two sums, then of course LMI linear of X is equal to the original LMI, which is actually affine, minus LMI of 0, which is a constant matrix, such as this one. So we will discuss, for instance, scaling, then we'll need to make that kind of separation, because we will be able to extract out the scaling factor only on the left LMI L fragment of the whole linear, but actually affine matrix inequality. So good, once this structure of our object of study has been clarified, if we recall examples, well, polyhedra were LMI sets, because scalar inequalities are just 1 times 1 matrix inequalities. Quadratics were also LMI sets, and well, we may have other convex shapes, such as this egg or something like that, whose boundary is cubic, as the determinant of this matrix is a degree 3 polynomial. So good, these are the LMI sets. Then, as we said, LMIs can be divided into a constant and a truly linear term. And in fact, if the constant term is 0, for instance, then the LMI set is a cone, because then the LMI is truly linear, so that if X renders the associated matrix positive semi-definite, then any positive scaling of X will result in an LMI that is the same matrix multiplied by that positive number. So if this is not there, if this is positive definite, so it is when I multiply by 2, because, well, the scaling can get out of here, 2, 3, 5, so it will be positive semi-definite for any positive multiple of X. So we will have a ray, let's say, going from 0 to infinity. So the LMI set will be a cone. Good. The thing is that if we are going to discuss transformations of LMI sets, then if we have, say, this affine transformation, X belongs to some LMI set, then if I build Z as this transformation of X, well, then as Z minus Q is Tx, T minus 1, Z minus Q is X. So if I just replace that in the argument of the LMI, then I have the new LMIs that the Z variable must verify. So that's it. The rest is, implementation detail, nothing theoretically important. But well, in order to show some of these transformations, we will concentrate in scaling and convex hull and some things like that. So let us detail some examples. And yes, we will first discuss how to scale an LMI set. And well, if I have the set of this, then if Z is lambda x, well, x is lambda minus 1z. So this is the LMI that Z must fulfill. But well, as the LMI can be split as a sum of a truly linear LMI, LMI sub L, and the constant matrix, LMI of 0, then I will get this to be LMI L lambda minus 1z plus this constant matrix F0 or LMI 0. And then if I multiply by lambda, being lambda a positive scaling, then multiplying by a positive scaling, a positive semidefinite matrix keeps it being positive semidefinite. So then this lambda can enter the truly linear part, and this thing will be equal to this thing as lambda, and lambda minus 1 will get cancelled. So this will be an equivalent way of writing this thing. And well, actually, as the linear part of the LMI is the full LMI minus the constant term LMI of 0, then replacing this by this, we can see that the positive scaling of an LMI set can be written as this thing for a fixed lambda. So let's see some example. And in this code, if you forget about x0, we'll speak about it in a minute. I will call tt2 the LMIs of 0. I will call tt1 the whole LMIs, and then each of the LMIs of the original set will be replaced by the linear part plus lambda minus 1, the constant part, in that line at the bottom, which is implementing this expression like here. So if I define the LMIs for an egg as this matrix being positive definite, then I will plot the scaling size 1, size 0.5, and size 0.25, and here I get the scalings. And also, if lambda is not a constant but a decision variable, and I tell lambda to be an interval with both non-negative ends, say this thing, then this LMI set will be a lifted one whose projection will be the union of all those scalings, and that will be a cone if I put a photographic camera at the origin throwing rays through the LMI set. So for instance, a cone between 0 and 1 scaling will be this set of 3 LMIs, one which will be a matrix 1 and 2 scalar ones, 1 times 1 matrices. And as LMI minus LMI of 0 is the linear part, then this first expression will be linear in Z, this second expression is linear in lambda, so if everything is linear, then the set is a cone, as we discussed some minutes ago. So good. If I tell that lambda must be between 0 and 1.5, and lambda is the decision variable, then building the LMIs of that scaled set with the variable lambda gets me the blue LMI set in the figure when I project over the 2D space. So the original egg size 1 is in red, I have two smaller scalings, and then I have the union of all scalings from 0 to 1.5. So the blue thing is like the projection of a 3D cone, being lambda, the height of the projection screen. So good. What happens if we wish to scale with the apex of this cone or its projection being in a different point instead of at 0? Well, we could just change the origin of coordinates with some straightforward transformations, or well, if we do them as follows, then we will reach this conclusion that is just, instead of putting here the LMI of 0, we put the LMI of the apex we wish for the position of the camera taking the pictures, let's say, because the transformation scaling with a new origin of coordinates, let's say, well, I will have that origin point x0, and then I will scale the increment from that x0. So when lambda is 1, then I will have z equal x. And when lambda is greater or smaller than 1 or whatever, I will have, the perspective from the point x0. And then as x will be this thing, if I place this thing as the argument of the LMIs and I separate it into the linear and constant part multiplied times lambda positive scaling and carry out some operations, you can just pause and inspect what we did, or download the materials from the link in the description. Well, the thing is that at the end, this is the scaling, let's say, shrinking towards x0. Or if lambda is an SDP var, a decision variable, this will be a lifted with one more dimension set, which will be, a perspective cone, and projecting that onto 2D, we will have this kind of picture in which this is the new scaling point instead of the origin we used in the previous simulation. As I said, you can just inspect the code. So we have these 3 scalings and the 2D projection of a 3D perspective cone. Good. The last thing we are going to show is interpolation and convex hull of LMI sets, in the sense that, look, here we are computing the convex hull, let's say, of the original egg, and the point in here, it is the projection of a cone, but it is also the convex hull. But, can we replace this x0 by another LMI set? Yes, indeed, we can. If we recall what is the direct sum of 2 LMI sets, then if chi1 belongs to LMI set 1 and chi2 belongs to LMI set 2, and z is the sum of those things, then the feasible points z, xi1 and xi2 of these conditions define the direct sum of that LMI sets. But okay, we can eliminate chi2, get these two LMIs. So projecting onto the z dimensions, we will get the direct sum. Then the interpolation between two sets will be expressing z as the sum of chi1 in a set scaled lambda and chi2 in the second set scaled 1 minus lambda. So when lambda is 1, we will have S1. When lambda is 0, we will have S2. And when lambda is 0.36, we will have something in between. So if we just replace this condition with the scaling formula we saw a few minutes ago, and we replace this thing with the scaling formula, instead of lambda, 1 minus lambda, we get this, and we also eliminated chi2, z minus chi1, to put it there. So these two LMIs give me the interpolation between two sets, and if lambda is a decision variable, then the union of all these interpolations for lambda between 0 and 1 will be the convex hull of two LMI sets. So if I set the code that given some LMIs, I scale the first ones by scaling factor lambda, and I scale the second ones with, this stuff by scaling factor 1 minus lambda, then I get new LMIs defining that interpolation or convex hull, depending on lambda being a constant or a decision variable. So if I define some triangle, and the egg we were using in prior plots, well, for lambda equal 0.55, if I build the interpolation LMIs and I plot them, let me put axis equal, then I get that the egg is on top, the triangle is at the bottom, and the 55% triangle, 45% egg is the cyan one. If I now go to 85% triangle, I get this new set, or if I go to 90% egg, 10% rectangle, I get that thing. So I get this kind of interpolation between sets, and in fact I generated several frames of a video of morphing from egg to triangle. Here we have it. So you can see how, as the interpolation coefficient evolves, we move from the egg to the triangle with this set interpolation concept. Then, if I let lambda be a decision variable, I force lambda to be between 0 and 1, we will get the convex hull of triangle and egg, which I depicted here. So we finish with this. In this video, we discuss scaling of LMI sets and the perspective cones in one more dimension, let's say, of such sets, as a particular case of affine transformations of such sets. Also, the direct sum of suitable scaled sets allowed me to express the convex hull of two sets with LMIs, and allowed me to introduce the concept of interpolation between two convex sets, defining such interpolation with LMIs. So with this, we end the video here. Thanks for your attention.